Hello and welcome. Before we begin our journey among the stars, make sure to subscribe so you never miss a calm exploration of the universe. Tonight, we'll guide your mind gently through the cosmos, observing extraordinary objects like black holes, quasars, and wandering planets. Not to frighten, but to understand. Every distant light, every invisible force follows precise, measurable laws, and with curiosity as your guide, the universe becomes a place of wonder and clarity. Let's settle in, relax, and begin our serene journey into the vast and remarkable world of space. You rest your attention on the idea that the universe is not designed to comfort or frighten you. It simply exists, unfolding according to physical laws that remain constant across space and time. When scientists describe something in space as terrifying, they are not speaking emotionally. They are referring to extremes that push matter, energy, and structure beyond everyday experience. Vast distances, immense masses, intense radiation, and overwhelming forces can feel unsettling because they challenge the scale your mind evolved to understand. You learn that danger in astronomy is measured carefully. Mass tells scientists how strongly an object bends space and pulls on nearby matter. Energy reveals how much radiation or motion it can release. Density shows how tightly matter is packed, sometimes compressing atoms themselves. Temperature indicates how violently particles move. These are calm, precise quantities, observed through telescopes, detectors, and mathematical models. Nothing in space acts with purpose. There is no intention, only interaction. When you look up at the night sky, most of what you see appears still and peaceful. Stars shine steadily. Planets trace slow paths. Yet beneath that calm appearance, powerful processes unfold. Gravity shapes galaxies. Nuclear fusion burns inside stars. Magnetic fields twist and stretch across enormous distances. These forces are not hidden, only distant. Science brings them closer by translating light and particles into understanding. You notice how the word terrifying often reflects human perspective rather than cosmic reality. A supermassive object does not threaten everything around it. A region of intense radiation does not spread unpredictably. The universe is structured. Objects follow orbits. Energy flows along defined paths. Even the most extreme environments obey equations tested again and again through observation. Predictability replaces chaos when you look closely. Astronomers spend decades measuring faint signals to understand these extremes. They track the motion of stars near invisible centers. They analyze tiny shifts in light caused by gravity. They detect particles arriving from distant explosions. Each measurement adds detail, not drama. The story that emerges is consistent. The universe does not escalate without reason. It evolves through well-understood processes acting over immense time. You consider how human intuition struggles with scale. A force that feels gentle on Earth can become overwhelming when extended across stellar masses. Gravity that holds you comfortably on the ground also binds galaxies together. Radiation that warms your skin can strip atoms apart when concentrated. These are differences of degree, not kind. The same physics applies everywhere. When something is described as dark in space, it often means unseen rather than malicious. Darkness can refer to regions that emit little light, objects that absorb more energy than they release, or forces that act without direct visibility. Scientists use instruments to extend vision beyond human senses. Radio waves, X-rays, gamma rays, and gravitational waves reveal environments your eyes alone cannot detect. Darkness becomes information. You learn that Earth is not exposed without protection. The planet's atmosphere absorbs harmful radiation. Its magnetic field deflects charged particles. Distance itself acts as a shield, reducing the intensity of even powerful cosmic events. While extreme objects exist, they are separated from you by vast expanses of space. The same laws that allow danger also ensure stability. Understanding begins to calm the initial tension. Fear thrives on uncertainty, but astronomy replaces uncertainty with measurement. When scientists identify a powerful object, they determine how far away it is, how fast it moves, and how its influence spreads. These details matter. They show that intensity decreases with distance. They show that interactions are limited by physical constraints. You reflect on how the universe appears indifferent because it does not adapt to observers. Stars do not change behavior when studied. Radiation does not pause when measured. This indifference can feel unsettling, yet it also means consistency. The same experiment produces the same result. The same physical law applies everywhere. Reliability becomes a quiet form of comfort. As you settle deeper into the science, you realize that the word terrifying often marks the edge of understanding rather than danger itself. Objects seem frightening when they stretch imagination beyond familiar limits. Once described through mass, energy, and motion, they become part of a coherent system. Extremes remain extreme, but they are no longer mysterious. You begin to sense how learning shifts perception. The universe does not grow darker as knowledge increases. Instead, patterns emerge. Structures repeat at different scales. Forces interact in predictable ways. Even destruction, such as stellar collapse, follows known sequences. Nothing appears suddenly without cause. This gentle realization allows your mind to rest. Space is vast, powerful, and sometimes harsh, but it is also orderly. The same laws that permit extreme environments also maintain balance across billions of years. As you remain with these ideas, you notice how curiosity replaces unease, and how the quiet structure of the universe invites steady attention rather than fear. You settle into the idea of black holes as regions of space where gravity becomes so strong that ordinary motion no longer applies. They form when massive stars exhaust nuclear fuel and collapse under their own weight. As the core compresses, gravity overwhelms all known forces that resist it. The result is a compact object whose mass remains, while its volume shrinks dramatically. Astronomers do not see black holes directly, because no light escapes from within a specific boundary. Instead, you learn how their presence is revealed by effects on nearby matter, light, and motion. Stars orbit unseen centers. Gas heats and glows before disappearing. Space itself bends in measurable ways. These observations provide consistent evidence that black holes exist, behave predictably, and follow equations tested across many environments repeatedly by independent teams using telescopes, detectors, and careful analysis across decades of observation and verification worldwide today now calmly consistently. You learn that the defining feature of a black hole is the event horizon, a boundary set by gravity alone. It marks the distance from the center where escape velocity equals the speed of light. Nothing crossing this limit can return information outward. This does not mean space suddenly ends there. Physics outside remains familiar. Objects fall inward following curved paths shaped by spacetime geometry. Time itself slows relative to distant observers, an effect predicted by general relativity and confirmed by experiment. From far away, infalling matter appears to fade and redden, never quite crossing. From its own perspective, the fall proceeds normally. These descriptions come from mathematics tested in laboratories and from astronomical measurements of orbiting stars and emitted radiation gathered patiently over time, reinforcing confidence that these effects are real, repeatable, and consistent with every reliable observation made so far by science today worldwide, now gently measured again. You notice that black holes are not uniform in size. Some form from stars only a few times more massive than the Sun. Others sit at the centers of galaxies with masses millions or billions of times greater. These supermassive black holes grow by merging with others and by accreting surrounding gas. Their gravity organizes entire galaxies, influencing star orbits and gas flows. Evidence comes from precise tracking of stellar motion near galactic cores. In the Milky Way, stars move rapidly around an unseen central mass. Calculations show that only a compact object can explain such speeds without flying apart. This conclusion arises from careful measurement, not dramatic assumption, repeated consistently across many galaxies using infrared telescopes, spectroscopy, and long-term observation that confirms stability over decades of time without contradiction or anomaly anywhere. Observed today calmly, now measured precisely again by astronomers worldwide, continuously, quietly, steadily, carefully, reliably, always. You also learn what black holes do not do. They do not wander randomly seeking matter. Their influence decreases with distance like any gravitational field. A black hole with the mass of the Sun would affect Earth no differently than the Sun itself if placed in the same location. Objects must come very close to experience extreme effects. This understanding removes a common fear. Black holes do not swallow galaxies indiscriminately. They remain bound by orbital mechanics and conservation laws. Even dramatic images often represent simulations designed to show invisible processes. The underlying physics remains calm, predictable, and consistent with long-tested principles supported by equations, observations, and repeated verification across decades of research that steadily refine understanding without overturning foundational results or introducing uncertainty beyond measured limits ever observed in space environments known today by science worldwide, quietly, continuously measured again and again, patiently, calmly, always reliably, now present. You consider what happens near the center, often called a singularity. This term indicates where current theories no longer fully describe conditions. Density appears infinite in mathematical models, signaling the need for more complete physics. Scientists acknowledge these limits openly. Outside this region, predictions remain accurate. The event horizon shields unknown interior behavior from influencing the external universe. This separation preserves consistency in observed physics. It shows how science distinguishes between what is measured and what remains theoretical. Admitting uncertainty does not weaken understanding. It defines its boundaries carefully and honestly through precise language, testable models, and constant comparison with observation, so confidence remains proportional to evidence rather than assumption or imagination at any scale examined by modern astronomy today, worldwide, calmly measured, consistently across time, again and again, patiently, reliably, always, gently, now present. Science practice accepted broadly by consensus, community members everywhere, now quietly, together, informed deeply. Continually. You learn how black holes are detected through gravitational waves, ripples in spacetime produced when massive objects merge. These waves travel at the speed of light and stretch space minutely as they pass. Sensitive detectors on Earth measure these changes precisely. Observations match predictions from relativity with remarkable accuracy. Each detection confirms mass, spin, and distance of merging black holes. This method does not rely on light, expanding how the universe is studied. Soundless and invisible, these signals provide calm confirmation of violent cosmic events far away, safely separated by distance, ensuring no physical effect reaches planetary environments like Earth beyond measurable background influence already understood and accounted for by existing models and protective natural systems present here today, quietly, always functioning reliably without disruption from such distant occurrences ever observed scientifically so far by humanity, now calmly aware. Attentive, informed, collectively, worldwide, steadily listening, precisely measuring, patiently, again, always. You reflect on how black holes challenge intuition without threatening stability. They reveal how gravity behaves under extreme conditions, extending known laws rather than breaking them. Each discovery refines models instead of overturning them. Far from symbols of chaos, black holes become tools for testing physics. They help measure cosmic distances and probe spacetime itself. The fear once attached to them fades as details accumulate. What remains is a quiet respect for the consistency of natural law operating even at its limits, confirmed by repeated observation, mathematical agreement, and long-term study across different environment scales, and epochs of the universe observed through multiple independent methods that converge reliably without contradiction anywhere known today by astronomy science practice worldwide, calmly, now accepted broadly, and taught carefully to ensure understanding remains grounded, precise, and steady over time, always present knowledge base for humanity collectively here, now quietly learning, continuously, deeply together. You settle into the idea that black holes are part of the universe's natural inventory. They are endpoints of stellar evolution and anchors of galaxies. Their behavior is constrained, not arbitrary. They do not represent the universe turning hostile. They represent the universe expressing gravity fully. This distinction matters. When fear is replaced by measurement, the unknown becomes approachable. Curiosity softens edges. Understanding provides rest through clarity, repetition, and steady exposure to evidence that builds confidence slowly, gently, without urgency or alarm, allowing your mind to relax into trust of physical law operating everywhere equally without exception or surprise across cosmic scale today, known measured consistently by science practice worldwide, calmly present now as knowledge continues expanding patiently outward into deeper understanding of space and time that remains stable, reliable, and deeply ordered beneath surface impressions, always quietly. So here you rest, aware, informed, gently, now listening attentively, peacefully still. You remain with the calm awareness that gravity can compress matter far beyond everyday experience. Black holes show one outcome, but not the only one. Other stellar remnants pack mass tightly while remaining observable. In these objects, atoms themselves are altered, yet surfaces still exist and signals still escape. They demonstrate another boundary where pressure rivals gravity without complete collapse. The universe offers multiple natural laboratories for studying matter under stress. As your thoughts settle, the idea of density itself becomes quieter and more precise, preparing your mind to consider how matter behaves when crushed almost, but not entirely, beyond recognition in conditions measured through observation, theory, and experiment that reveal limits without mystery while remaining accessible to careful study by astronomers, physicists, and instruments designed to detect subtle effects across space and time, calmly present today, now inviting steady curiosity without fear or urgency, simply attention and rest gently. You focus on neutron stars, remnants left behind after the core of a massive star collapses in a supernova. Their mass is comparable to the sun, yet squeezed into a sphere only about 20 kilometers across. You imagine how tightly matter is packed, though your mind can barely hold the scale. 1 teaspoon of neutron star material would weigh billions of tons on Earth. Gravity overwhelms the forces that normally keep atoms apart. Electrons merge with protons, forming neutrons. The result is an object that is almost entirely neutrons, dense beyond ordinary comprehension, yet predictable through well-tested nuclear physics and equations of state that describe matter under extreme pressure with remarkable consistency. You observe how neutron stars rotate. Many spin hundreds of times per second, a rate preserved from the collapsing core's angular momentum. This rapid rotation produces measurable effects on nearby matter and radiation. Some neutron stars emit beams of radio waves along magnetic poles. These beams sweep across space like a lighthouse, appearing to pulse when aligned with Earth. Astronomers detect these signals with radio telescopes, allowing them to determine spin rate, magnetic field strength, and distance. Each pulse arrives with precision, confirming the regularity of their rotation and providing a calm rhythm to what might otherwise seem chaotic. You consider their magnetic fields. Neutron stars possess some of the strongest known in the universe, reaching trillions of times the strength of Earth's field. These magnetic fields influence charged particles in the surrounding environment, producing X-rays and gamma rays. Observations of these emissions provide insight into surface temperature, field orientation, and composition. Despite their intensity, these effects remain spatially constrained. They diminish with distance according to established electromagnetic principles, so proximity is required to experience them directly. At the scale of Earth's orbit, the influence is imperceptible, allowing you to appreciate the extremity without danger. You notice that neutron stars are remarkably stable. Once formed, their mass, rotation, and magnetic properties evolve slowly over millions of years. Tiny irregularities in spin, called glitches, occur occasionally. These are predictable, small adjustments due to interior processes, such as the movement of superfluid neutrons or crustal shifts. Each observation adds to your understanding of dense matter physics. Through decades of radio and X-ray astronomy, scientists have measured thousands of neutron stars, each reinforcing theoretical predictions. You perceive a quiet order underlying the seemingly extreme conditions. You learn about the surface environment. Neutron star crusts are solid, formed from tightly packed nuclei. Beneath lies a layer of superfluid neutrons, behaving like a frictionless fluid under immense pressure. Calculations of thermal conduction, shear strength, and magnetic stress allow scientists to model how energy propagates through these stars. Observed X-ray emissions confirm predictions. Even in such extreme compression, matter responds consistently to known physical laws. There is no unpredictability beyond measurable quantum and nuclear effects, making these stars reliable laboratories for understanding extreme physics in real time. You reflect on how neutron stars emit energy. Rotational kinetic energy gradually slows as radiation carries angular momentum away. Pulsars, the spinning, beaming neutron stars, release energy in a steady, observable manner. Measurements of these losses match theoretical models closely. Their radiation does not spread randomly but follows predictable trajectories and intensities. You recognize that even the most extreme outputs are constrained by mathematics and observation. The universe demonstrates its power methodically, not capriciously. You consider how neutron stars interact with companions in binary systems. Matter from a nearby star can be drawn toward the neutron star, forming an accretion disk. The infalling material heats to millions of degrees, emitting X-rays detectable from Earth. These systems provide a controlled context to observe gravity, magnetic fields, and relativistic effects in action. Each observation reinforces predictability, showing how mass, velocity, and energy interrelate. There is no chaos outside the parameters defined by physics. Extreme does not mean uncertain. You notice the gravitational effects of neutron stars on surrounding space. Their compact mass warps spacetime noticeably. Orbits of nearby objects deviate according to general relativity, and these deviations are measurable with current technology. Pulsar timing can even detect distant companions or gravitational waves. Each measurement agrees with predictions, demonstrating that neutron stars, despite their density and rotation, remain consistent and understandable within well-tested frameworks. Space bends, matter responds, and observation confirms expectation. You contemplate the matter inside. The pressure at the core is so high that nuclear interactions dominate. Protons and neutrons are packed nearly as tightly as physics allows. Yet, despite extreme density, models of equation of state predict size, mass, and behavior accurately. Observational confirmation comes from mass measurements through binary systems, gravitational lensing, and pulsar timing. No exotic, unmeasurable effects have been observed that contradict these models. You feel reassurance in the precision of nature, even at conditions vastly beyond terrestrial experience. You rest with the thought that neutron stars, though extreme, are part of the universe's structured hierarchy. They occupy a middle ground between ordinary stars and black holes. Their predictability allows scientists to test theories under conditions unreachable on Earth. Observing them connects you to forces operating at densities and pressures unimaginable in daily life. You sense how extreme environments do not equate to danger, but instead provide insight and calm understanding through measurement and repeatable observation. Your awareness expands to consider how matter itself can be pushed to its limits and still respond to physical law. Neutron stars reveal the boundaries of atomic and nuclear structure. They demonstrate how energy, rotation, magnetism, and gravity coexist harmoniously even under extraordinary circumstances. Each pulse, each orbit, each X-ray emission reinforces that matter, no matter how compressed, obeys predictable patterns. You notice how extreme density provides a mirror to study other objects and phenomena in space with precision. You feel the weight of scientific understanding as a gentle guide. Extremes no longer intimidate but inform. Observations, timing, and calculations illuminate the physical rules governing dense stars. Through patient measurement and interpretation, what first seems beyond comprehension becomes approachable. Even in their vast difference from everyday experience, neutron stars offer a structured, reliable, and peaceful view of matter under intense gravity, offering clarity without alarm. Their existence quietly hints at further lessons about how matter can behave under force and motion, preparing your mind to consider the interplay between energy, gravity, and the cosmic extremes that continue to shape the universe calmly, consistently, and measurably. You focus on magnetars, a rare type of neutron star distinguished by their magnetic strength. These objects possess magnetic fields trillions of times stronger than Earth's, concentrated over a sphere only about 20 kilometers in diameter. You imagine how field lines wrap around the star, twisting and interacting with charged particles in its vicinity. Although the intensity is extreme, it follows predictable physics. Electromagnetic theory and quantum mechanics describe the structure and strength of these fields. Observations confirm theoretical predictions, showing that magnetars behave consistently within understood limits, even under conditions far beyond ordinary experience. You notice how magnetars are detected. Astronomers rely on X-ray and gamma-ray emissions, which arise from the interaction of the magnetic field with the star's surface and magnetosphere. These emissions pulse regularly, often corresponding with rotation. Detectors in orbit capture these signals, measuring intensity, frequency, and spectrum. Each observation provides data about magnetic strength, rotational period, and energy output. The consistency of pulses demonstrates that, despite extreme conditions, magnetars follow predictable patterns, governed by fundamental laws that are verified across multiple observational platforms and decades of data collection worldwide today quietly, steadily, consistently. You learn that magnetars rotate more slowly than typical neutron stars, often spinning once every 2 to 12 seconds. Their strong magnetic fields gradually slow rotation over time, converting rotational energy into electromagnetic radiation. These processes are measurable, allowing scientists to track age and activity levels. Occasionally, magnetars undergo starquakes, subtle shifts in the crust caused by magnetic stress. These events produce short bursts of X-rays or gamma rays. Even these bursts follow well-understood physical principles, and their energy is constrained by the star's mass, magnetic field, and structure. You perceive how extreme activity remains bounded and measurable, offering both challenge and clarity to observers. You consider the effect of a magnetar's field on nearby space. Close to the star, charged particles spiral along magnetic lines, emitting radiation. Farther away, field strength diminishes with distance according to the inverse cube law. A magnetar would have no noticeable effect on Earth at ordinary distances in the galaxy. Scientists calculate safe distances using classical electromagnetism and observational data. These calculations show that even the most powerful magnetars pose no direct hazard to planets far from their immediate vicinity. The universe remains orderly, and intensity is contained within precise boundaries, measurable and predictable without speculation. You observe how energy emission is maintained. Magnetic stress induces currents in the outer crust and magnetosphere. Energy stored in the field is gradually released through electromagnetic radiation, producing persistent X-ray luminosity. Occasionally, sudden reconnections of magnetic lines generate intense bursts. Satellites detect these as soft gamma repeater events or anomalous X-ray pulsations. The intervals, energies, and spectra match predictions from magnetohydrodynamics and crustal physics. These events repeat in patterns that can be studied, modeled, and understood, reinforcing the notion that the cosmos, even in extremes, operates under consistent laws rather than random behavior. You notice that magnetars provide unique laboratories for physics. The extreme density and magnetic strength test quantum electrodynamics in regimes unreachable on Earth. Observations of particle behavior, radiation emission, and surface activity allow theorists to refine models of matter under extreme pressure and field intensity. Pulsed emissions, energy decay, and quiescent luminosity all serve as data points in understanding fundamental interactions. These processes are not dangerous to observers at typical distances but offer insight into conditions that push atomic structure toward limits. You sense how careful measurement transforms potential unease into structured understanding. You consider the star's magnetic decay. Over tens of thousands of years, the field weakens, reducing rotational braking and surface stress. The energy output gradually diminishes, and bursts become less frequent. By comparing multiple magnetars, astronomers estimate lifetimes, field decay rates, and evolutionary pathways. The slow timescale allows for long-term observation without urgency or surprise. Patterns emerge across populations, providing a calm consistency that deepens understanding of stellar evolution and electromagnetic processes, reinforcing that even the most extreme phenomena evolve predictably. You reflect on surface conditions. Crustal stress from magnetic forces is immense, yet confined within the solid lattice of nuclei. The outer layer, though only a few hundred meters thick, experiences pressures sufficient to fracture, producing measurable starquakes. Emission patterns from these events match predictions from nuclear and solid-state physics. Deep internal layers remain largely inaccessible, but the observable surface demonstrates that extreme magnetic and gravitational forces do not imply chaos. Instead, the behavior aligns closely with well-established physical models. You learn that magnetars, though visually dramatic in data plots, emit energy following precise trajectories. Radiation beams and particle motion are constrained by field geometry. Satellites detect flux variations, spectra, and timing with high accuracy. Astronomers use this data to map field strength, orientation, and evolution. Every observation confirms the predictability of extreme magnetism. Knowledge replaces uncertainty, and patterns provide reassurance. You sense the quiet balance in systems that, at first glance, might seem violent or erratic. You consider how these objects influence their surroundings over longer timescales. Stellar winds from nearby stars can interact with magnetic fields, producing localized emission and slight orbital adjustments. Accretion from companions, when present, follows predictable gravitational and electromagnetic principles. The extreme environment is localized and constrained. Farther away, space-time and matter remain unaffected. These measurements emphasize that intensity diminishes with distance and that even the most extraordinary phenomena operate within understandable bounds. You feel calm as precision, measurement, and lawfulness transform extremity into knowledge. You rest with the awareness that magnetars exemplify nature's extremes without unpredictability. Mass, rotation, and magnetic strength define behavior. Radiation, surface stress, and bursts are all measurable consequences. Observations reinforce theoretical predictions. The universe displays its power systematically, not arbitrarily. By studying magnetars, you gain insight into matter under extraordinary stress, electromagnetic interaction at unparalleled strengths, and the stability of physical laws. Extremity does not equal danger. It equals opportunity to observe the consistency of nature under extraordinary conditions. You feel a gentle sense of continuity as you consider how the dense matter of neutron stars interacts with extreme magnetism. The combination of pressure, rotation, and electromagnetic force provides a foundation to understand even greater releases of energy, extending naturally toward phenomena capable of unleashing extraordinary amounts of radiation across vast distances, quietly inviting attention and reflection without alarm. As the universe continues to reveal structure in every extreme measured today calmly and consistently across space. You focus your attention on the final stages of massive stars, approaching a moment when the core can no longer sustain itself against gravity. In stars more than 8 times the mass of the Sun, nuclear fusion eventually produces iron at the core. Iron cannot release energy through fusion, so the balance between outward pressure and inward gravity collapses. The core contracts rapidly, electrons and protons combine into neutrons, and the central region becomes a neutron-dense core. This process initiates a core collapse supernova, releasing energy on a scale that outshines entire galaxies for weeks. Observations of light curves, neutrino emissions, and expanding shells of matter confirm these events repeatedly, providing consistent, evidence-based data about the underlying processes. You notice how the outer layers respond. As the core contracts, shock waves propagate outward through the star's envelope. Material accelerates to thousands of kilometers per second. The expanding gas becomes ionized, emitting visible light and higher energy radiation detectable across space. Telescopes capture this radiation, allowing astronomers to reconstruct the explosion's energy, mass ejection, and velocity. Even though the release of energy is immense, it is constrained by the star's mass, composition, and radius. Physical laws dictate the expansion rate and light emission, producing patterns that can be predicted, modeled, and confirmed by repeated observations over decades. You learn that not all supernovae originate from core collapse. Type Ia supernovae occur in binary systems where a white dwarf accumulates matter from a companion. Once the mass approaches the Chandrasekhar limit of about 1.4 solar masses, the white dwarf can no longer support itself. Thermonuclear reactions ignite almost simultaneously throughout the star, resulting in a violent explosion. These events produce characteristic light curves and spectra, allowing astronomers to identify them with precision. Type Ia supernovae serve as standard candles for measuring cosmic distances, demonstrating that even extreme events provide structured, measurable data for scientific understanding. You reflect on the production of elements. Supernovae synthesize elements heavier than iron through rapid neutron capture processes, known as the R process. Observations of spectral lines in remnants confirm the presence of elements like gold, platinum, and uranium. These heavy elements are then distributed into the surrounding interstellar medium, contributing to future generations of stars and planets. The process is governed by nuclear physics and confirmed by laboratory measurements of reaction rates and decay processes. Even the creation of matter on such a vast scale follows consistent, measurable laws. You observe the impact on the surrounding environment. Shock waves compress nearby gas clouds, triggering star formation in some regions. The expelled material enriches interstellar space with new elements, influencing the chemical composition of subsequent stellar generations. Expansion velocity, composition, and interaction with interstellar gas can be measured with spectroscopy and radio imaging. The dynamics are entirely predictable given initial conditions, illustrating that violent events in space are structured outcomes of physical principles rather than random chaos. Each supernova leaves a long-lasting, observable imprint that scientists can study with clarity and precision. You notice the range of supernova energies. Core collapse events release roughly 10 to the power of 44 joules of energy, mostly carried away by neutrinos, which escape almost unimpeded. A smaller fraction manifests as light and kinetic energy, which we can detect directly. Type Ia supernovae are slightly less energetic but produce remarkably uniform light curves, allowing cross-validation with models. Observations of remnants, light curves, and neutrino detections repeatedly confirm theoretical predictions, reinforcing the stability and reliability of the models used to describe these extreme stellar events. You learn how remnants evolve. A supernova can leave behind a neutron star, a magnetar, or, if the progenitor was massive enough, a black hole. The expelled envelope forms a supernova remnant, expanding into space at predictable velocities. Observations of remnants such as the Crab Nebula reveal filamentary structures and radiation patterns consistent with models of expansion, shock heating, and magnetic field interaction. Each measurement reinforces understanding of the physics involved. No aspect of the process behaves unpredictably beyond quantum-scale variations. The remnants serve as laboratories for studying plasma, magnetism, and nuclear reactions under extreme conditions. You consider how supernovae are observed in real time. Modern surveys scan the sky nightly, detecting sudden brightening events. Astronomers record spectra, luminosity changes, and environmental context. Each detection is logged and analyzed, providing data for decades of cumulative understanding. The rate of occurrence, spatial distribution, and light curve characteristics match theoretical expectations based on stellar populations and evolutionary timescales. Patterns emerge clearly, allowing scientists to predict where and how often such events are likely to occur without any need for speculation or assumption beyond verified models. You notice the effect on galaxies. Supernovae contribute to the regulation of star formation, the distribution of metals, and the dynamics of interstellar gas. Their energy input stirs interstellar turbulence, compresses gas clouds, and influences the rotational behavior of galactic material. Observational surveys show consistent correlations between supernova rates and galactic properties. These relationships arise naturally from physical interactions rather than intentional processes. The apparent violence of a supernova is integrated into a predictable galactic ecosystem that can be measured, modeled, and understood with precision. You reflect on how energy is conserved. The total energy released, partitioned among neutrinos, light, kinetic motion, and heat, always matches predictions from nuclear and gravitational models. Neutrino observations from nearby supernovae confirm theoretical outputs. Even when the visible explosion is spectacular, the energy distribution adheres to physical law. Nothing occurs spontaneously or unpredictably. Observation and theory converge, providing reassurance that extreme events in space follow understandable, measurable rules, allowing curiosity and attention to replace uncertainty or unease. You learn that observing supernovae is also a window into time. Light from distant explosions takes years, sometimes millions, to reach Earth. You are effectively seeing events long past, yet all physics remains consistent. By comparing multiple observations, astronomers refine models of stellar evolution, mass loss, and explosion mechanisms. Each supernova provides a piece of a larger puzzle that is consistently assembled through patient, repeated measurement. Extremes, when studied calmly, produce structure rather than chaos. You settle with the understanding that supernovae, while immensely energetic, are governed entirely by the laws of physics. Their creation of heavy elements, emission of radiation, and influence on galaxies follow predictable, measurable patterns. Observation, modeling, and repeated verification transform what might feel dramatic into a quiet, structured system. The universe releases energy in magnitude and sequence, but always within the bounds of known principles. Awareness of these processes allows the mind to appreciate scale without fear, and to anticipate that matter and energy continue to follow ordered, measurable paths even in the most violent cosmic events, gently leading to the idea of the most energetic flashes observed across vast distances. You direct your attention to gamma-ray bursts, extraordinary events detected across the cosmos. These bursts release in seconds as much energy as the sun emits over billions of years. They occur when massive stars collapse or when neutron stars merge. Instruments in orbit capture the brief, intense gamma-ray emission, recording its spectrum, intensity, and temporal structure. Each detection provides precise information about the energy output, duration, and distance. Observations are repeated across multiple satellites, confirming that bursts follow predictable, measurable physical processes even at such extreme energy scales, and their behavior is consistent with the laws of relativity and quantum physics. You notice that gamma-ray bursts are classified by duration. Long bursts, lasting more than 2 seconds, are generally linked to the collapse of massive stars, producing black holes. Short bursts under 2 seconds are associated with collisions between neutron stars or a neutron star and a black hole. Each type generates distinct light curves and energy distributions, which astronomers can measure with high precision. By observing repeated events in different regions of the sky, scientists confirm that both types of bursts are governed by the physics of extreme gravity, relativistic jets, and high-energy particle interactions. These measurements allow careful predictions of their frequency and properties. You learn how gamma-ray bursts emit energy in focused jets. Radiation is concentrated along narrow cones, moving near the speed of light. Earth is safe from most bursts because the jets must align precisely with our position to register as a detection. Satellites record only a small fraction of the total number of bursts occurring across the observable universe. The intense energy diminishes rapidly outside the jet, illustrating how magnitude is constrained by geometry and distance. Even events with power unimaginable on Earth operate within predictable physical limits, and their influence is localized to extremely narrow regions of space. You observe the afterglow of gamma-ray bursts. Following the initial flash, X-rays, ultraviolet, and visible light are emitted as jets interact with surrounding gas. Observatories track these afterglows to determine the burst's position, energy, and the density of the surrounding interstellar medium. Light curves decay predictably, confirming models of relativistic shocks and radiation processes. Observations across multiple wavelengths consistently reinforce understanding of the mechanisms. The afterglow serves as a natural clock and diagnostic tool, revealing details about the burst without introducing randomness or chaos into the system. You consider the detection process. Space-based instruments such as the Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory monitor the sky continuously. Each burst triggers automated measurements of duration, intensity, spectrum, and location. Follow-up observations refine distance calculations through redshift, confirming that these events occur in galaxies billions of light-years away. Neutrinos and gravitational waves have also been associated with some short bursts, providing complementary data. The convergence of independent measurements ensures that interpretations remain robust, and uncertainties are limited to instrumental precision, not conceptual error. You reflect on the physical mechanisms. In long-duration bursts, the collapsing star forms a black hole or neutron star, while angular momentum drives relativistic jets along its rotational axis. In short-duration bursts, merging compact objects release gravitational energy that converts into highly collimated gamma-ray emission. The underlying physics is described by relativistic hydrodynamics and quantum electrodynamics, providing equations that match observations accurately. Laboratory simulations, mathematical modeling, and numerical computation support satellite data, confirming that extreme energy release remains governed by consistent, measurable laws. You notice that gamma-ray bursts influence galaxies locally. Jets deposit energy into the surrounding medium, compressing gas, and producing observable emission in X-rays and radio waves. Yet these effects are limited spatially. Observations indicate that the most intense energy is confined to the jet path and nearby surroundings. Farther regions of the host galaxy experience ordinary gravitational and radiative environments. Even these violent events integrate into galactic evolution in ways that can be measured and predicted, demonstrating that energy, no matter how extreme, is constrained by distance, geometry, and physical law. You learn about the role of distance in perception. Most bursts occur billions of light-years away, meaning their energy is observed long after emission and over vast volumes of space. Even if a jet were directed toward Earth, its distance would reduce impact to levels easily absorbed by our atmosphere and magnetic field. Models confirm that catastrophic exposure is extremely improbable. Measurements of nearby galaxies have not indicated direct hazard from gamma-ray bursts within the past hundreds of millions of years. Observation ensures that knowledge of intensity, frequency, and geometry provides reassurance and clarity. You observe that gamma-ray bursts provide insight into cosmology. Their brightness allows measurement of intergalactic medium absorption and distance scaling. Light interacts predictably with intervening matter, revealing the chemical composition of distant galaxies and the expansion of the universe. Each event functions as a natural laboratory for relativistic physics, nucleosynthesis, and gravitational interactions. While individually extreme, bursts collectively provide orderly information that deepens understanding of astrophysical processes. You consider energy distribution. Most of the burst's energy is carried in gamma-ray photons moving near the speed of light. The remaining energy appears as kinetic energy of ejected matter or in afterglow radiation. Observations confirm that total energy output remains consistent with models. Variations between bursts are predictable based on progenitor mass, rotation, and environmental density. Each measurement matches expectations derived from theory, reinforcing the principle that even the universe's most powerful explosions operate under calculable laws. You reflect on their rarity. Although billions of stars exist in every galaxy, gamma-ray bursts are observed only occasionally from each system. The combination of mass, rotation, and collapse conditions is uncommon, and precise alignment is required for detection on Earth. Astronomers compile statistical models using historical observations and sky coverage, confirming expected occurrence rates. The infrequency contributes to the safety and stability of the universe while allowing study of extreme phenomena without hazard. The calm order of rarity and distance reinforces the sense of a measured, reliable cosmos. You settle with the understanding that gamma-ray bursts are both immense and precise. They emit extraordinary energy, yet their impact is spatially and temporally constrained. Observations across multiple instruments and wavelengths allow scientists to describe them quantitatively. Distance, geometry, and physics together limit the effect on distant observers, turning extreme phenomena into measurable, comprehensible events. Awareness of these processes provides perspective, showing that the universe can release immense power safely and predictably, and that even the sharpest flashes are part of a structured cosmic order, quietly preparing the mind to consider solitary, wandering worlds that traverse space without stellar companions. You imagine a planet traveling through the darkness of interstellar space, untethered to any star. These objects, called rogue planets, have been ejected from their original solar systems or formed independently in isolation. Without a host star, they receive no constant energy, so their surfaces are extremely cold. Temperatures can drop to just a few degrees above absolute zero, leaving them in near total darkness. No sunlight warms them. No day or night cycles mark their passage. Despite this, they remain massive, bound by their own gravity, maintaining a spherical shape and internal pressure consistent with their size and composition. Their existence is inferred, not seen directly, which creates a subtle sense of mystery grounded entirely in observation and measurement. You learn how astronomers detect these elusive planets. One of the primary methods is gravitational microlensing, which relies on Einstein's theory of general relativity. When a rogue planet passes between a distant star and Earth, its gravity slightly bends and magnifies the light from that star. The resulting brightening occurs for a short, measurable period, often lasting days or weeks. Careful analysis of the light curve allows scientists to estimate the planet's mass, distance, and sometimes even size. Multiple surveys over years, using networks of telescopes across the globe and in space, confirm these events repeatedly. Each detection is rare but precise, demonstrating that invisible objects can be studied without direct observation, entirely through their measurable gravitational effect. You notice that the majority of rogue planets are likely smaller than Jupiter, though some could rival the gas giants of our solar system in mass. Their composition can vary from rocky, dense cores to thick layers of hydrogen and helium. Some may retain a small internal heat source from radioactive decay, slowing their cooling over billions of years, but overall they remain extremely cold compared to planets orbiting stars. Observations and modeling of microlensing events allow scientists to estimate population statistics, showing that the Milky Way may host billions of these wandering worlds, quietly moving through space without affecting their surroundings in any immediate way. You reflect on the dynamics that create rogue planets. They can be ejected from forming solar systems through gravitational interactions with other planets or stars. During the early stages of planetary system evolution, close encounters can transfer enough energy to launch a planet into interstellar space. Alternatively, some may form in isolation from dense molecular clouds, never acquiring a central star. The mechanisms are understood through simulations and long-term observations of planetary systems. The results are predictable outcomes of Newtonian and relativistic gravity, not random chaos, allowing the universe to remain comprehensible even at its extremes. You consider the potential hazard of these bodies. Unlike asteroids or comets, rogue planets are large but move slowly relative to stars and planets. Their danger lies not in aggression or destructive power but in invisibility. They can traverse space silently, potentially passing near other systems, but close encounters with Earth are extremely improbable. Orbital mechanics and probability models indicate that the likelihood of a rogue planet striking our solar system is vanishingly small over the lifetime of the Sun. Their presence introduces subtle gravitational effects in distant star clusters, but these influences are measurable and calculable rather than threatening. Observation replaces uncertainty with reassurance. You notice how detection limits constrain our knowledge. Rogue planets do not emit light in the visible spectrum, making them essentially invisible to ordinary telescopes. Infrared observations can detect residual heat, but only for relatively nearby examples. Microlensing remains the most effective method for studying distant objects, though each event is temporary. Statistical models derived from these detections estimate the number, size distribution, and spatial density of rogue planets. Even with limited data, astronomers achieve robust conclusions about the population, demonstrating that the unseen universe can be mapped methodically and accurately, without speculation or fear. You learn about their internal structures. Like planets in a solar system, rogue planets may have layered interiors, a core of rock or metal, surrounded by mantle and crust, or, in the case of gas giants, dense hydrogen-helium envelopes. Internal heat can drive limited geologic activity or convection, even in the absence of a star. Magnetic fields may still exist, generated by motion in conductive cores, and could influence any surrounding charged particles. These features, although largely theoretical, are consistent with known physics and observed in planetary bodies within our own system, providing confidence that the same principles apply to untethered planets traveling through interstellar space. You consider how rogue planets interact with other objects. Occasionally, they pass through dense regions of gas, star clusters, or molecular clouds. Their gravity can slightly alter the motion of nearby stars or smaller planets, but these interactions are subtle and predictable. Simulations of galactic dynamics show that such encounters are extremely rare and generally minor in effect. Observations of stellar kinematics provide indirect evidence supporting these predictions. Rogue planets exemplify how even unanchored bodies obey consistent gravitational laws, and how distant and massive objects can move through space without disturbing it significantly or unpredictably. You notice that some rogue planets could harbor subsurface oceans, insulated by internal heat or thick ice layers. If liquid water exists, chemical interactions could occur independently of sunlight, though any biological implications are purely speculative. Observational evidence for such conditions is limited but consistent with thermal modeling and planetary physics. The concept reinforces that extreme environments exist without violating physical laws, and that temperature, pressure, and material properties can be predicted accurately. These possibilities remain calm and measurable, rather than alarming. You reflect on how the study of rogue planets advances astronomy. Each microlensing detection improves understanding of planetary formation, galactic population density, and interstellar dynamics. Surveys reveal the frequency of ejections from solar systems, refining models of planetary system evolution. Observations confirm that these bodies are not anomalies but expected outcomes of gravitational processes acting over millions of years. Through careful measurement, astronomers transform invisibility into knowledge and unpredictability into a structured picture of galactic populations. You settle into the quiet fact that space can be crowded with massive objects moving silently, yet this does not imply danger. Rogue planets remind you that the universe contains objects whose presence is inferred rather than directly observed. Observation, physics, and statistical analysis allow astronomers to map them without fear. Their darkness, coldness, and slow motion are not threats but features measurable through precision instruments and validated models. Awareness of their existence expands your understanding of planetary systems and the vast variety of objects inhabiting the galaxy, calmly preparing your mind to observe smaller, faster-moving celestial bodies that cross Earth's neighborhood with measurable frequency. You rest with the knowledge that rogue planets, despite their size and invisibility, operate entirely within predictable physical law. Their motion, gravity, and interactions can be modeled and observed. Awareness replaces uncertainty, and the silence of these wandering worlds does not conceal danger, only curiosity. Space, even when crowded with unseen objects, is orderly and measurable. Each detection, each measurement, adds structure to what was once unknown. The universe contains mysteries, but each is approachable through patience, observation, and adherence to physical law, leaving you ready to contemplate smaller, more immediate objects that drift across the solar system, still guided by gravity and calculable motion. You begin by observing the small bodies that share our solar system, asteroids and comets. Asteroids are primarily rocky or metallic fragments, remnants from the early formation of the solar system. Most orbit the Sun in the asteroid belt between Mars and Jupiter, moving predictably along elliptical paths. Their sizes range from a few meters to hundreds of kilometers. Comets, in contrast, are composed largely of ice, dust, and volatile compounds. Their orbits are often highly elliptical, taking them from the distant reaches of the solar system to the inner regions near the Sun. Both types of objects follow the precise rules of celestial mechanics, which allows scientists to calculate their trajectories accurately and predict interactions with planets, including Earth. You notice that near-Earth objects are defined as bodies whose orbits bring them within 1.3 astronomical units of the Sun. Astronomers catalog these objects, measuring orbital parameters such as semi-major axis, eccentricity, and inclination. By applying Newtonian gravity and perturbation theory, scientists can forecast positions decades into the future. Ground-based telescopes and radar observations refine these measurements. The data reveals that while thousands of near-Earth asteroids exist, the probability of a collision with Earth in any given year remains very low. Risk is quantifiable, not mysterious, and observation reduces uncertainty. You learn how impact history informs understanding. Craters on Earth and the Moon record past collisions. Large impacts, such as the Chicxulub crater formed 66 million years ago, illustrate that collisions are rare but significant. Smaller impacts occur frequently, producing meteorites that reach the surface without major consequence. Scientists study these remnants to understand composition, speed, and trajectory at entry. Measurements of impact craters, combined with orbital models, allow calculation of probabilities and potential damage. Knowledge of size-frequency distribution and historical occurrence reassures that while impacts happen, their scale and frequency are predictable. You observe asteroid composition. Metallic asteroids contain iron and nickel, while stony asteroids are silicate-rich. Some contain carbon compounds, providing insight into early solar system chemistry. Spectroscopic observations reveal surface materials, reflecting light at characteristic wavelengths. Radar imaging further determines shape, rotation, and surface roughness. Each measurement allows scientists to classify asteroids into families, improving models of orbital evolution and potential Earth encounters. Comet composition is studied through spectroscopy and space missions, detecting gases released as they approach the Sun. Both types of objects follow physical rules that are consistent and measurable. You notice how orbital dynamics influence collision risk. Jupiter's gravity plays a significant role, perturbing asteroid paths and injecting some into Earth-crossing orbits. Resonances and close encounters with planets alter trajectories gradually, in ways that can be calculated precisely. The Yarkovsky effect, a subtle force caused by uneven heating, slightly changes asteroid orbits over decades. By incorporating these forces into models, astronomers refine long-term predictions. Even seemingly chaotic motion remains deterministic under classical mechanics, allowing systematic assessment of which objects pose potential hazard. You learn about monitoring programs. Surveys such as NASA's Near-Earth Object Observations Program, PANSTARRS, and the Catalina Sky Survey track asteroids nightly. Automated telescopes measure brightness, position, and motion. When a new object is detected, calculations determine its orbit, size, and impact probability. Follow-up observations refine predictions, often years in advance. If a potential impact is identified, the path can be modeled decades ahead, giving ample time for mitigation planning. The process transforms potential uncertainty into actionable knowledge. You consider comets and their unpredictable appearances. Long-period comets originate in the Oort cloud, taking thousands of years to complete an orbit. While their motion is influenced primarily by gravity, small jets of gas from sublimating ice can slightly alter paths. Scientists account for these effects using repeated observations and modeling. Short-period comets from the Kuiper belt are more regular, and their trajectories are easier to forecast. In each case, understanding motion and composition allows astronomers to assess risks reliably. Surprises are rare and measurable in advance. You observe detection techniques. Radar can map surface shape, rotation, and velocity. Infrared observations reveal size and albedo, clarifying whether an object is dark and reflective or dense and metallic. Spectroscopy identifies chemical composition, confirming whether the body is likely to survive atmospheric entry. Each method complements the others, providing a comprehensive dataset for each near-Earth object. The universe, even in its crowded regions, is systematically mapped, and each object's path is understood through repeatable measurement. You notice that probability, not immediate danger, governs your awareness. Objects tens of meters across could cause local damage, while kilometer-scale impacts are exceedingly rare. Statistically, such events occur on scales of thousands to millions of years. Researchers quantify these probabilities, producing risk tables and visualizations for public understanding. Science transforms anxiety into measured assessment, and Earth's atmosphere acts as a shield for smaller objects, burning them before reaching the surface. Observation, probability, and physics combine to reduce uncertainty. You learn about mitigation strategies. Techniques for planetary defense include kinetic impactors, gravity tractors, and precise deflection. Simulations model how altering an asteroid's path by even a few meters per second decades in advance can prevent collision. Monitoring programs and international collaboration ensure that potential hazards are identified and addressed long before they become imminent. The calculated and controlled approach allows the mind to relax, knowing that risks are understood and managed through physics, observation, and careful planning. You reflect on the role of continuous observation. New discoveries and improved technology constantly refine understanding. Each year adds data points that clarify orbit evolution, composition, and risk. Analysis of past impacts informs models for future prediction. You perceive that while space contains countless small bodies, the majority remain non-threatening due to predictable paths and slow evolution. The statistical framework provides a calm perspective, replacing fear with understanding of measurable probabilities. You settle with the understanding that asteroids and comets, though capable of significant energy release upon impact, follow laws that are quantifiable and observable. Their motion, composition, and potential effects can be tracked, measured, and modeled over decades. Danger is statistical, not sudden, and knowledge transforms uncertainty into clarity. Awareness of these silent travelers allows a steady appreciation for the processes shaping Earth and the solar system, as well as confidence that the universe operates according to predictable rules. The mind rests easily, noting that even objects with potential to disrupt are part of an orderly, measurable cosmic system, preparing attention for the more distant, energetic phenomena that illuminate entire galaxies with their light. You direct your attention to quasars, some of the brightest objects in the observable universe. Quasars exist at the centers of galaxies, powered by supermassive black holes millions to billions of times the mass of the Sun. These black holes draw in surrounding matter, forming an accretion disk of gas, dust, and plasma spiraling inward. Friction and gravitational forces heat this material to millions of degrees, producing radiation across the electromagnetic spectrum, from radio waves to visible light, X-rays, and gamma rays. Observations of these emissions allow astronomers to measure the energy output, infer the mass of the black hole, and understand the physics of extreme gravity and matter. You notice that quasar light travels across billions of light-years before reaching Earth. Observing a quasar is effectively looking back in time, seeing the galaxy as it was when the light first began its journey. Spectroscopic measurements reveal redshift, indicating the expansion of the universe and allowing calculation of distance. Astronomers use these data to map the distribution of quasars throughout cosmic history. Each observation reinforces the principle that light propagates predictably through space, interacting with intervening matter according to well-understood physical laws, providing a window into both extreme energy processes and the evolution of the universe. You learn how accretion disks operate. Matter falling toward the black hole forms a flattened, rotating disk due to conservation of angular momentum. Viscosity within the disk converts kinetic energy into heat, emitting intense radiation. The inner edge of the disk lies close to the event horizon, where gravitational and relativistic effects become extreme. Observations of spectral lines, variability in brightness, and emission profiles confirm the structure of these disks. Models based on magnetohydrodynamics and general relativity describe how matter moves, radiates, and eventually crosses the horizon, demonstrating that even at extreme energies, processes follow precise, measurable physical laws. You observe relativistic jets that sometimes emerge from quasars. Magnetic fields generated in the accretion disk can channel particles away from the black hole's poles at speeds approaching the speed of light. These jets emit radiation along narrow paths that can extend thousands of light-years. Observing jet orientation and brightness helps astronomers understand the geometry of the quasar and the spin of its black hole. Jets interact with surrounding interstellar gas, producing shocks and synchrotron emission detectable across multiple wavelengths. These interactions follow predictable physical laws, providing a laboratory for studying matter under extreme conditions. You consider the scale of energy involved. A single quasar can emit as much energy as hundreds of normal galaxies combined. Despite this vast power, the effects on Earth are negligible due to the immense distances involved. By measuring flux, redshift, and spectrum, astronomers calculate luminosity and energy output with high precision. Observations of variability in quasar brightness over days, months, and years allow study of accretion physics and black hole dynamics. The universe demonstrates that extreme phenomena can exist safely at sufficient distance, while still providing measurable insights into fundamental physics. You learn how quasars inform cosmology. Their light passes through intergalactic space, encountering gas clouds and galaxies along the way. Absorption lines in quasar spectra reveal the chemical composition, density, and motion of intervening matter. By analyzing many quasars across different redshifts, scientists map the large-scale structure of the universe and the evolution of galaxies over billions of years. Patterns emerge consistently, showing that even the most luminous, distant objects operate under predictable physical processes that provide reliable data about the cosmos. You notice that quasars vary in brightness. Changes occur due to fluctuations in accretion rates, instabilities in the disk, or relativistic effects near the black hole. Light curves record these variations, offering insight into disk structure, temperature gradients, and magnetic activity. Observations across multiple telescopes and wavelengths provide a full picture of quasar behavior. Despite immense complexity, models accurately describe these variations, reinforcing that the extreme environment is governed by measurable laws rather than unpredictability or chaos. You reflect on the formation of supermassive black holes. Current evidence suggests they grow through both accretion of surrounding matter and mergers with other black holes. Observations of quasars at very high redshifts indicate that massive black holes formed within the first billion years of the universe. Astronomers use simulations and statistical modeling to understand growth rates, accretion efficiency, and feedback mechanisms. Each finding confirms that even extraordinary phenomena follow processes that can be studied, measured, and reproduced in simulations, providing structure to extreme cosmic activity. You consider quasar host galaxies. The interaction between the black hole and surrounding stars affects star formation and galactic evolution. Powerful radiation and jets can heat gas, suppressing star formation in some regions, while triggering it in others. Observations of galactic morphology, gas dynamics, and star populations support these conclusions. The feedback mechanisms operate consistently according to gravity, thermodynamics, and electromagnetic principles. This balance demonstrates how energy at enormous scales integrates naturally into galactic systems, without introducing randomness beyond calculable perturbations. You notice the observational techniques used. Telescopes in optical, infrared, radio, and X-ray bands capture different aspects of quasars. High-resolution imaging resolves jets and host galaxy structure. Spectroscopy measures chemical composition, temperature, and velocity fields. Variability monitoring tracks accretion and jet behavior. Each technique reinforces others, providing a consistent understanding of quasars as extreme yet structured systems. Data from multiple instruments around the world and in orbit ensures that interpretations are accurate, verifiable, and replicable. You learn that quasars illuminate more than just their own energy. Their light serves as a probe of cosmic history, revealing intergalactic gas, dust, and large-scale structure. By mapping absorption features and comparing redshifts, astronomers reconstruct the distribution of matter and the growth of galaxies over billions of years. The intensity of quasars, though extreme, becomes a tool for understanding processes far beyond their immediate environment. Knowledge replaces potential apprehension, showing that even the universe's most energetic objects contribute to a comprehensible, orderly picture of cosmic evolution. You settle with the understanding that quasars, despite their extraordinary energy output, follow predictable laws of gravity, electromagnetism, and thermodynamics. Observation, modeling, and spectroscopy provide precise information about structure, dynamics, and history. Distance ensures safety while allowing insight. Awareness of these luminous giants demonstrates that extreme phenomena are measurable, predictable, and integrated into the evolution of the universe. The mind rests with curiosity satisfied, ready to consider the subtler, pervasive influence of invisible particles and radiation that silently traverse space, carrying information across the cosmos without disruption or harm. You direct your attention to cosmic radiation, a constant presence throughout space. Cosmic rays consist of high-energy particles, primarily protons and atomic nuclei, that travel at near-light speeds. They originate from a variety of astrophysical sources. Supernova remnants accelerate particles through shock waves, while active galactic nuclei emit energetic jets that contribute to the highest energy cosmic rays. Observations using satellite detectors, ground-based arrays, and balloon experiments measure their energy, composition, and arrival direction. Despite their speed and energy, these particles interact with matter according to known physical principles, allowing scientists to quantify their properties accurately. You notice that cosmic radiation is present everywhere, yet most passes unnoticed. The particles traverse vast distances between stars, interacting only occasionally with gas or magnetic fields. When cosmic rays collide with interstellar atoms, they generate secondary particles that can be detected with specialized instruments. Observations of these interactions confirm the origin, energy, and flux of the primary particles. Detectors such as the Pierre Auger Observatory and AMS-02 on the International Space Station provide continuous measurements, showing that the intensity and spectrum of cosmic rays are consistent and predictable across time. You learn how Earth's atmosphere provides natural protection. As cosmic rays enter the atmosphere, they collide with air molecules, producing showers of secondary particles that are mostly absorbed before reaching the surface. The resulting radiation at ground level is low, measurable, and generally harmless. Detectors confirm that background radiation from cosmic rays contributes only a small fraction to natural radiation exposure. Measurements across different altitudes and latitudes reveal predictable variation, with higher exposure at mountain elevations or near the poles, due to the geometry of Earth's magnetic shielding. You observe the role of Earth's magnetic field. Charged cosmic rays are deflected by the magnetosphere, which funnels high-energy particles toward the poles while shielding equatorial regions. Satellite measurements show that the strength of this deflection depends on particle energy and charge. Variations in the geomagnetic field, such as those associated with solar activity, slightly alter fluxes, but the effects remain within measurable and predictable limits. The protective role of the magnetic field demonstrates a stable, physical barrier against otherwise high-energy phenomena, reducing risk while providing valuable data for space science. You consider secondary radiation produced in the upper atmosphere. When cosmic rays collide with nuclei in air molecules, they generate muons, neutrons, and pions, forming a cascade of particles that travel downward. Ground-based detectors capture these secondary particles, allowing scientists to reconstruct the energy and type of the original cosmic ray. The process is fully understood within particle physics and verified by repeated experiments. Observations confirm that the atmosphere significantly reduces the intensity of high-energy particles reaching the surface, keeping their effects measurable, stable, and non-threatening to life under normal conditions. You learn about cosmic background radiation, the relic photons from the early universe. Detected as microwave radiation uniformly distributed across the sky, the cosmic microwave background carries a record of conditions 380,000 years after the Big Bang. Satellites like COBE, WMAP, and Planck measure its temperature fluctuations with high precision. These fluctuations reveal information about the distribution of matter, the growth of cosmic structures, and the overall geometry of space. Although faint, this radiation permeates space and provides a constant, measurable signal that informs cosmology without posing hazard. You notice radiation from the sun, which contributes lower-energy cosmic particles and electromagnetic radiation. Solar flares and coronal mass ejections increase particle flux temporarily, but satellites monitor these events continuously. Spacecraft measure proton and electron intensities, allowing accurate prediction of their effects on instruments and astronauts. Earth's magnetic field and atmosphere further mitigate these contributions. Solar radiation adds to the natural background, but with predictable variations that can be quantified and anticipated using well-established physics. You observe how cosmic rays influence matter over long timescales. Interactions with molecules in space or the atmosphere can produce isotopes such as carbon-14, which is used for dating archaeological and geological samples. Measurements of these isotopes correlate with cosmic ray intensity, solar activity, and geomagnetic changes. The production rate is calculable, providing a precise tool for scientists rather than an unpredictable hazard. Understanding these interactions converts otherwise invisible energy into measurable, informative signals about both terrestrial and cosmic processes. You learn that high-energy cosmic rays are extremely rare. Particles with energies above 10 to the power of 20 electron volts strike Earth only once per square kilometer per century. Detectors across the globe observe these events, confirming that even the most energetic particles occur on predictable scales. Their interactions with the atmosphere and instruments provide insights into particle physics beyond what is possible in terrestrial accelerators. Measurements consistently match theoretical predictions, demonstrating that the universe's most extreme radiation is both measurable and statistically constrained. You consider implications for space travel. Outside Earth's protective shields, astronauts are exposed to higher cosmic radiation. Shielding, mission planning, and monitoring reduce exposure and maintain safety within well-defined limits. Models of particle flux, energy distribution, and shielding effectiveness are based on experimental data and physical principles. By applying these techniques, cosmic radiation becomes a manageable factor in exploration rather than a mysterious threat. Observing its intensity and effects reinforces understanding of particle physics and space environment dynamics. You notice how cosmic radiation helps map the galaxy. Detection of energetic particles allows inference of sources and trajectories. Observations of anisotropy, energy spectra, and composition inform models of supernova remnants, galactic magnetic fields, and star-forming regions. Each measurement contributes to an orderly understanding of the mechanisms that generate, accelerate, and distribute high-energy particles. Repeated observation confirms that these processes, while extreme, are consistent and governed by physical law, reinforcing the predictability of phenomena that might otherwise seem random. You reflect on the stability of cosmic radiation. Despite occasional solar storms or nearby supernova events, the overall flux remains steady over decades. Scientists track long-term variations, allowing prediction of trends and exposure. Knowledge of this radiation environment transforms potential fear into measurable data. Instruments, calculations, and models convert invisible particles into quantifiable, understandable information. Observation turns what could be threatening into a reliable tool for studying space and cosmic processes. You settle with the understanding that cosmic radiation is pervasive, energetic, and constant, yet fully predictable and manageable. Earth's atmosphere and magnetic field provide protection, while observations reveal sources, flux, and interactions with matter. Each measurement reinforces that the invisible universe operates under precise laws. Awareness replaces uncertainty, showing that energy and particles traverse space without threat, quietly informing your understanding of astrophysical processes. You rest in the knowledge that even invisible hazards are mapped, quantified, and understood, leading the mind toward the unseen mass shaping galaxies, waiting to be measured through gravitational influence rather than light. You focus your attention on dark matter, a substance that neither emits nor absorbs light, yet dominates the mass of the universe. Its presence is inferred entirely through gravitational effects on visible matter, radiation, and the motion of galaxies. Observations of spiral galaxies show that stars orbit faster at their edges than can be accounted for by visible mass alone. Measurements of rotation curves indicate that an additional, unseen component contributes the majority of gravitational influence. These observations, repeated across hundreds of galaxies, consistently confirm that dark matter exists and shapes cosmic structure without interacting electromagnetically, allowing space to remain safe while still revealing hidden mass. You notice how gravitational lensing provides evidence for dark matter. Light from distant galaxies bends as it passes near massive objects, a prediction of general relativity. Observing distortions in the shape of background galaxies allows astronomers to map mass distribution, including matter that cannot be seen. Clusters of galaxies show lensing patterns that require much more mass than luminous material alone. By carefully modeling these lensing effects, scientists produce maps of dark matter, revealing its influence on multiple scales, from individual galaxies to superclusters. This method offers a precise, repeatable way to detect and study what is otherwise invisible. You learn about galaxy clusters. Observations show that individual galaxies in clusters move faster than expected if only visible mass were present. X-ray measurements of hot gas in clusters provide additional mass estimates, which together with lensing results indicate a dominant dark matter component. These measurements allow precise calculation of the total mass of clusters, confirming that visible matter accounts for only a small fraction. The consistency of these findings across independent techniques strengthens confidence in the presence and distribution of dark matter. Its invisibility is not a hazard but a feature of how gravity organizes cosmic structure. You observe the formation of large-scale structures. Simulations based on cosmological models show that dark matter acts as a scaffolding for ordinary matter. Filaments, sheets, and voids emerge naturally as dark matter collapses under gravity. Galaxies form along these dense regions, while low-density regions remain largely empty. Observations of galaxy surveys confirm these patterns, revealing a cosmic web that aligns with dark matter predictions. Each measurement matches simulation, demonstrating that the unseen majority provides an orderly framework for the universe, measurable and consistent despite its invisibility. You notice the role of dark matter in individual galaxies. Its gravitational influence prevents stars at the outer edges from escaping. Rotation curves show a flat profile, meaning orbital velocity remains nearly constant with increasing distance from the center. These observations contradict expectations based solely on visible mass but are consistent with a dark matter halo surrounding the galaxy. The halo is diffuse, extending far beyond the visible disk, and is measurable through careful modeling of stellar motion. Awareness of this structure allows you to understand how galaxies maintain cohesion, even when much of their mass is unseen. You learn how dark matter interacts with ordinary matter. Unlike cosmic rays or radiation, dark matter does not collide, absorb, or emit light. Its presence is sensed only through gravity. Observations confirm that it passes through ordinary matter without disruption, making it safe yet influential. Experiments designed to detect weakly interacting massive particles, WIMPs, or axions attempt to measure rare interactions, but so far, direct detection remains elusive. The lack of electromagnetic interaction ensures that dark matter's influence is indirect but fully measurable through its gravitational effects. You consider evidence from the cosmic microwave background. Fluctuations in temperature and density in the early universe reflect the interplay between radiation, ordinary matter, and dark matter. Detailed measurements by satellites such as Planck reveal a consistent ratio of dark matter to ordinary matter, roughly 5:1. These fluctuations set the initial conditions for the formation of galaxies and large-scale structure. Analysis of these data confirms that dark matter is a dominant component in the universe, shaping evolution in predictable ways without posing direct threat to any observer. You notice how simulations model dark matter distribution. N-body simulations calculate gravitational interactions between millions of particles, representing dark matter in a virtual universe. Results match observations of galaxy clustering, rotation curves, and lensing patterns. These simulations allow scientists to explore variations in dark matter properties and the resulting structure formation. Repeated agreement between simulated and observed structures strengthens confidence that dark matter's effects are fully consistent with known physical laws. Its invisibility is not chaotic but orderly and predictable. You learn about dwarf galaxies and satellite systems. Many small galaxies appear to be dominated by dark matter, with minimal luminous material. Observations of stellar motion reveal mass far exceeding visible components. These systems provide high-precision laboratories for studying dark matter density profiles, core versus cusp structure, and potential interactions with ordinary matter. Analysis of multiple dwarf galaxies reinforces the conclusion that dark matter shapes structure consistently at both large and small scales, demonstrating predictability even in faint, hard-to-observe systems. You observe gravitational lensing in clusters once again. Detailed mapping shows both concentrated and diffuse dark matter components. Observations of merging clusters, such as the bullet cluster, reveal that dark matter passes through collisions largely unaffected, while ordinary gas interacts electromagnetically and slows down. The separation between visible and unseen mass is measured precisely, providing direct evidence of dark matter's distinct behavior. Observational consistency ensures that theoretical models remain aligned with empirical data, turning uncertainty into quantifiable understanding. You reflect on how dark matter influences galactic evolution. Its presence stabilizes disks, regulates star formation indirectly, and contributes to the gravitational potential that binds clusters. Over cosmic time, dark matter acts as the silent organizer of matter, guiding galaxies into coherent structures. Observations across multiple wavelengths, coupled with simulations, provide repeated confirmation of its role. This hidden framework allows the universe to maintain order while remaining largely invisible, reassuring that what is unseen operates predictably. You notice ongoing research into particle properties. Experiments underground, in orbit, and using high-energy accelerators seek rare interactions, refining understanding of mass, cross-section, and behavior under extreme conditions. Results so far constrain possible candidates without implying hazard. The scientific process demonstrates patience and precision, showing that even the unknown can be approached methodically. Observation and modeling together allow exploration of the invisible majority with confidence and calm curiosity. You settle with the awareness that dark matter, though unseen, provides measurable, essential structure to the universe. Its gravitational influence explains galactic rotation, lensing effects, and the cosmic web. Detection is indirect but precise, and observation replaces fear with knowledge. Even the unseen can be understood through repeated measurement and modeling. You rest in the understanding that the universe contains vast, invisible components, their presence governing structure in a predictable, safe, and orderly fashion, gently guiding attention to the subtle but pervasive force that accelerates the cosmos itself. You turn your attention to the large-scale structure of the universe and the observation that it is expanding. Galaxies are not merely moving within space. Space itself stretches between them. This expansion was first measured in the 1920s through observations of galactic redshifts, showing that distant galaxies recede from us, with velocity proportional to distance. Later, precise measurements of type Ia supernovae, which serve as reliable standard candles, revealed a surprising detail. The expansion is accelerating. This phenomenon is attributed to a component of the universe called dark energy. Despite its name, dark energy is not visible or directly detectable. It is inferred from the way cosmic expansion changes over time. You notice that dark energy constitutes roughly 68% of the total energy content of the universe, far exceeding ordinary matter and dark matter. Its presence is inferred from multiple independent lines of evidence, including supernova luminosity distances, cosmic microwave background observations, and large-scale structure surveys. Each method measures the effect of expansion over cosmic time. Although the underlying mechanism of dark energy is not fully understood, its influence on the dynamics of galaxies and clusters is measurable, consistent, and described mathematically in the context of general relativity. The universe expands gently but persistently, without irregularity or disruption. You learn how scientists measure expansion. Type Ia supernovae provide a consistent peak luminosity, allowing calculation of distance. Comparing the observed brightness with intrinsic luminosity yields precise measurements of how far away the explosion occurred. Combining these distances with redshift measurements gives the rate of expansion at different epochs. These results demonstrate that not only is the universe expanding, but the expansion rate has increased over the past several billion years. Observational data is precise, reproducible, and analyzed through well-understood physics, transforming a seemingly abstract concept into concrete, measurable quantities. You consider the mathematical framework. Dark energy is often described by the cosmological constant, introduced by Einstein, which represents a uniform energy density pervading space. In this model, the repulsive effect counteracts gravitational attraction on large scales, accelerating expansion without violating physical laws. Alternative models, such as quintessence, propose dynamic fields, but observations constrain variations, ensuring that the influence remains smooth and uniform. These frameworks allow calculations of the Hubble parameter, cosmic acceleration, and distance redshift relationships, all measurable and consistent with observation, providing predictability in what might otherwise seem mysterious. You observe the uniformity of expansion. Galaxies move away from each other in all directions, and the effect is proportional to distance. Nearby galaxies exhibit smaller relative velocity, while extremely distant ones recede rapidly. Importantly, expansion occurs in the space between structures, not within gravitationally bound systems such as galaxies or clusters. Their internal dynamics remain dominated by local gravity, unaffected by the global stretching. Observations confirm this distinction, demonstrating that expansion is gentle, pervasive, and measurable, not chaotic or destructive. You learn that the effect of dark energy is cumulative. Over billions of years, small accelerations accumulate, increasing the separation between galaxy clusters. Astronomers study the growth of cosmic voids, galaxy filament distribution, and cluster motion to quantify the influence. Simulations incorporating dark energy reproduce observed large-scale structures and expansion history. Each calculation matches observation, reinforcing that even a phenomenon that dominates the universe's energy budget operates according to principles that can be observed, quantified, and understood. You notice the role of the cosmic microwave background in constraining dark energy. Fluctuations in temperature and density reflect the universe's composition at recombination. Precise measurements allow calculation of the matter density and the fraction attributed to dark energy. This independent method complements supernova and large-scale structure observations, providing convergent evidence. Even though dark energy itself is invisible, its gravitational and expansion effects leave measurable imprints, confirming its existence consistently and predictably. You consider how acceleration affects the observable universe. Light from distant galaxies is stretched, increasing wavelength and redshift. Over extremely long periods, objects may move beyond the observable horizon, becoming undetectable, yet the effect is gradual and uniform. Observations of high redshift galaxies provide snapshots of earlier expansion states, creating a timeline that scientists can study. This process is governed entirely by the geometry of space, relativistic physics, and the distribution of matter and energy. Expansion is measurable, smooth, and comprehensible rather than abrupt or alarming. You learn about the interplay with dark matter. While dark matter shapes the formation of structures locally, dark energy dominates the global dynamics of expansion. Observations show that at smaller scales, galaxies and clusters remain bound, but at larger scales, repulsive effects of dark energy accelerate the separation of unbound systems. Measuring velocity dispersions, cluster mass distributions, and cosmic flows allow scientists to distinguish the contributions of dark matter and dark energy. This distinction clarifies that extreme forces in the universe are orderly, measurable, and consistent with theory. You notice that the acceleration of expansion has implications for the future universe. Models indicate continued growth, with large-scale structures moving farther apart. Observational data and simulations show that while distances increase, physical laws remain consistent, and local systems remain unaffected. The expansion is pervasive yet gentle, occurring over timescales far exceeding human perception. Scientists can measure rates, predict trajectories, and quantify cosmic influence, demonstrating that even the universe's largest-scale phenomena are understandable through careful observation and theory. You reflect on the subtlety of dark energy. Unlike radiation, cosmic rays, or visible mass, its presence is inferred from motion and geometry rather than direct detection. Observations of galactic redshifts, supernova brightness, and cosmic background fluctuations provide a coherent, measurable picture. Each measurement is reproducible, confirming that dark energy affects the universe in calculable ways. Despite its invisibility, its influence is consistent, smooth, and predictable, creating a gentle expansion that is safe, comprehensible, and deeply informative about the evolution of space itself. you consider the precision of modern measurement. Projects like the Dark Energy Survey, the Sloan Digital Sky Survey, and the Hubble Space Telescope gather detailed data on galaxy positions, luminosity, and distance. Analysis of these datasets produces statistical maps of expansion and acceleration. Repeated observations confirm that the rate of acceleration is consistent with predictions from the cosmological constant model. These precise measurements allow scientists to refine parameters continuously, reinforcing understanding and minimizing uncertainty. The universe, even at this scale, is measurable and orderly. You settle with the understanding that dark energy, though invisible and pervasive, manifests through measurable, predictable acceleration of cosmic expansion. Observations confirm its influence on galaxy separation, large-scale structure, and the overall geometry of space. Its presence is inferred through rigorous measurements rather than directly seen, yet its effects are fully consistent with physical law. Awareness of this gentle, uniform expansion transforms what could feel incomprehensible into structured knowledge. The mind rests with the certainty that even the vastest forces of the universe operate under rules that are observable, calculable, and reassuring, gently preparing attention for the perspective that knowledge transforms even the most extreme cosmic phenomena into clarity. You begin by noticing the vastness of space, stretching across distances so large that comprehension requires numbers, light years, and scales beyond daily experience. Yet within this immensity, understanding brings comfort. Objects that might seem terrifying, black holes, quasars, rogue planets, asteroids, cosmic radiation, dark matter, and dark energy, are all governed by precise physical laws. Each phenomenon follows predictable patterns that scientists have observed, modeled, and measured. Knowledge turns what might appear random into a comprehensible, stable system, where probability, force, and distance determine influence rather than intention or unpredictability. You reflect on black holes once imagined as purely destructive. Now you understand that their gravitational pull is intense yet localized. Observations show that only matter within a very specific range will cross the event horizon. Accretion disks, jets, and radiation are energetic, but safely distant from Earth. Light from billions of years ago carries data about their mass, spin, and environment, allowing calculation of interactions long before they could ever affect our planet. Knowledge converts the unknown into measurable properties, replacing instinctive apprehension with calm understanding. You consider quasars, whose extreme brightness can outshine entire galaxies. Their immense energy originates from matter spiraling into supermassive black holes. Despite this, the vast distance ensures that Earth experiences no danger. The light reaching our telescopes has traveled billions of years, showing early stages of galactic evolution. Observations of jets, accretion disks, and spectral emissions allow scientists to predict behavior with precision. Understanding their physics demonstrates that even the most luminous, energetic objects operate under laws that are measurable and consistent, and their effects are safely remote. You notice rogue planets drifting through interstellar space, invisible but not threatening. Detection through gravitational microlensing has revealed their existence, yet their impact on the solar system is negligible. Their danger lies in invisibility, not aggression. Asteroids and comets pose measurable risks, yet monitoring systems track their orbits decades in advance. Impact probabilities are calculated statistically, and the majority of small bodies burn in the atmosphere. Earth's natural protection and scientific vigilance provide reassurance, illustrating how systematic observation and modeling transform potential threats into known quantities. You reflect on cosmic radiation, passing constantly through space and matter. It has measurable intensity and composition, influenced by supernova remnants, active galaxies, and solar activity. Earth's atmosphere and magnetic field shield life from harmful levels, while detectors quantify variations with precision. Background radiation, high-energy particles, and secondary cosmic showers are constant yet predictable. Understanding energy, particle flux, and shielding removes uncertainty, showing that even invisible hazards can be characterized, studied, and safely managed. You contemplate dark matter, shaping galaxies and large-scale structures while remaining invisible. Observations of rotation curves, gravitational lensing, and cluster dynamics provide measurable evidence. Though unseen, dark matter's effects are predictable and fully integrated into models of structure formation. Its presence stabilizes galaxies, guides star formation, and influences cluster behavior. Unseen forces operate according to consistent gravitational laws, providing an orderly framework across the cosmos. Awareness of dark matter's role replaces unease with appreciation for underlying structure. You consider dark energy, gently accelerating the expansion of space itself. Measurements from supernovae, galaxy surveys, and the cosmic microwave background reveal a uniform, persistent effect. The acceleration is smooth, acting over billions of years, and does not interfere with local systems. Calculations and observations confirm its presence and quantify its impact on cosmic expansion. Understanding dark energy converts an invisible, vast force into a measurable phenomenon, demonstrating that even the largest-scale processes in the universe are orderly and comprehensible. You notice the interplay of observation and prediction across all these phenomena. Astronomy, physics, and cosmology rely on measurement, modeling, and repeated verification. Predictions are not guesses, they are calculated outcomes based on laws of gravity, thermodynamics, electromagnetism, and relativity. The universe may be immense and extreme, but the same principles apply everywhere. Statistical risk, distance, and natural shielding dictate influence, making apparent danger manageable. Knowledge reduces uncertainty, and careful observation allows you to perceive the cosmos with calm curiosity. You reflect on the human role in understanding. Telescopes, satellites, particle detectors, and space missions continuously gather data. Scientists analyze orbits, light, radiation, and gravitational effects, converting observation into prediction. Planetary defense programs, cosmic surveys, and deep space missions ensure that potential hazards are known long before they could become threats. Systems of measurement and verification provide reassurance that Earth is protected, not by luck, but by knowledge applied through science. Observation replaces fear with informed awareness, cultivating calm and curiosity. You consider scale and perspective. Cosmic events unfold over distances and times far beyond human experience. Supernovae, galaxy collisions, and black hole accretion operate over millions or billions of years. While locally insignificant, they provide invaluable data about the physics of matter, energy, and gravity. By studying these processes, you recognize that the universe is extreme yet consistent, powerful yet orderly, immense yet approachable through careful observation. Scale becomes a tool for understanding, not a source of anxiety. You notice patterns and structure in the cosmos. Galactic filaments, cosmic webs, rotation curves, and radiation signatures all display predictable behavior. Statistical models, simulations, and repeated measurement allow anticipation of cosmic events with increasing precision. The universe, while vast and occasionally intimidating in magnitude, is consistently governed by laws that can be studied and applied. This understanding creates a sense of calm, showing that what might seem threatening is, in fact, orderly, measurable, and approachable through reason. You reflect on cumulative knowledge. Each discovery, from asteroids to quasars, cosmic rays to dark energy, adds to a coherent framework that explains extremes without invoking unpredictability. Measurement, observation, and theory together form a comprehensive view of the cosmos. Fear diminishes when phenomena are understood quantitatively, and imagination rests in the clarity of physical law. Knowledge transforms potentially unsettling information into structured, digestible insights. You notice that curiosity becomes a guiding principle. Instead of anxiety, observation sparks questions that can be addressed through measurement, modeling, and calculation. The process of learning about the universe, observing patterns, and verifying predictions fosters calm attention. Each discovery provides reassurance that phenomena operate predictably and safely, even at scales far beyond human perception. Awareness of the universe's mechanics allows the mind to relax, knowing that extreme forces and distant hazards are managed by distance, probability, and physical law. You settle with the understanding that the universe, vast and extreme, is comprehensible through careful observation and reasoning. Black holes, quasars, asteroids, cosmic rays, dark matter, and dark energy all follow measurable, predictable rules. Risk is quantified, forces are understood, and distant phenomena pose no immediate threat. Awareness of natural protection, scientific vigilance, and consistent physical laws cultivates a sense of safety and calm. Knowledge transforms apprehension into curiosity, allowing the mind to rest within the vast, orderly expanse of space. You drift in recognition that understanding replaces fear, and the universe continues its processes quietly, steadily, and without harm.